Let's skip that then.
I wasn't there, but I remember hearing you talk about this.
I could do it for you right now. if you'd like.
Sure.
I don't have a black light with me, so I'll have to use my flashlight. It's not quite as good, but. So the lesson is the coupling of spin to angular minimum. So we mentioned yesterday that the rules are that angular minimum is 3.1, the spin can't change. So L equals 1 especially for atoms is really, really hard. The delta S equals 0 can break because of spin orbit coupling. And the example of that, there's lots of examples in the literature or in real life of this happening, but the most important one, or the one that I can demonstrate the most, is glow in the dark. The way that glow in the dark works. Let me just kind of talk you through this energy level diagram. We have a ground state.
Wait,
So-
let me find this on my.
It's not in your notes.
Oh, it isn't?
You weren't here with it.
Yeah, no, but I was on Zoom.
Oh.
Here it is. I got
Oh,
it.
yeah, you got it. Okay, yeah, so the stuff inside of the plots here is as a powdery paste kind of stuff, and it's an organic aromatic molecule ligand with strontium and europium atoms, doping. Okay, so
Okay.
there are the things that provide europium, strontium in particular. They have high energy, highly excited angular minimum electrons. They have a lot of spin orbit coupling.
Right.
So the atoms provide the spin orbit coupling to the organic ligands, which are the things that absorb the UV radiation.
Okay.
Okay, so the energy levels you're seeing here are excitations of the chromophore on the organic molecule inside the paste. And so there's a ground state that's spin singlet, which means all the electrons are paired, just a normal organic molecule.
Yeah.
And the idea is you excite it to an excited state. The excited electrons give a UV photon, right? So your sun shines at your material, it excites it to the excited state, which is still a spin singlet, but it's excited angular momentum, right? Orbital angular momentum. So it's like an S to a P or something like that, but spin is still 0, so everything's still paired. And that can immediately decay through fluorescence very quickly. I don't think I can show you the fluorescence because I don't have it. So if I had a UV light, you'd see these glow like crazy.
Oh,
So
okay.
they would look like they're reflecting the UV light. Right now, you can see they're not really reflecting anything other than some reflection of black.
Yeah.
But with the UV light, you see that they glow bright blue
Okay.
because they fluoresce out the radiation that you feed in.
I see.
But there is a forbidden intermediate state, which is a triplet, where the spin has split. That's sitting very close in energy to the excited state.
Yeah.
In order to get into that forbidden state, I need to flip the spin.
But with the.
So for-
But with the
Spin orbit.
spin orbit coupling, it can get.
Yes, spin orbit coupling breaks that delta S equals 0, but it's very rare. So for 1,000 molecules that come over here, only one comes over here.
Okay, I see.
It's a small percentage, but occasionally it breaks a rule and another one shows up over there. So now you have molecules trapped in this intermediate state. And they need to get back
Right,
down to the ground state.
forbidden.
And that's forbidden as well for the same reason this was forbidden.
Yeah.
But it's even harder to do this because they're so far from an energy.
Okay, I see.
So it would turn out the further apart it could be, the harder it is to facilitate that transition. So they get stuck in here. And so the rate of decay from, I'm sorry.
It's okay, I don't know why that.
That's because the rate of decay from this state to this state is extremely slow because it's forbidden. Whereas between this state and fluorescence is very fast because it's allowed.
Right,
It's just going backwards.
okay.
So you get this intermediate state, you get molecules stuck in here. And so you can imagine as you pump it with UV light, you're slowly moving molecules into
Into
here.
there.
And you're charging this state up and it slowly discharges and it's lower energy. So that means that this intermediate state, when it emits very slowly, it emits a longer wavelength. It's slower
Right.
energy.
So that's why you can't see it when the light is on, but when you turn off the light.
Yeah,
there's
so when
less
you
energy around.
charge it, so you can't see the fluorescence because I'm not really pumping it with a lot of UV photons. This is pretty much light.
Mhm.
But there are some UV photons in this light, and they will charge into that intermediate.
Oh, yeah, I
state.
see it.
And now you're seeing them emit, so it lasts a long time,
Mhm.
because the rate of decay there is 40.
Yeah, okay, got it.
So that's what's called phosphorescence.
Gosh, should I like redraw this note so that it's better like this one?
No, it's fine. It's just, I'm not really touching on this. This is just
Okay.
we're just exploring an application.
Yeah.
No, this is exactly the same reason how a plant cell and store electrical energy after sourcing a photon. UV photon.
Oh,
Photosynthesis. And those, the absorbers, I can't remember, what did they call it? The chlorophylls. The chlorophylls absorb that light, and of course they fluoresce. They fluoresce very rapidly, but they
Yeah.
fluoresce so rapidly that that energy that gets stored gets immediately dispelled. So there has to be
Right.
some way to store that energy for a long time. So
Okay,
you use that
that's
spin
what
orbit
makes
coupling transition like this,
Hmm.
where the excited state of the chlorophyll is coupled to some receptor protein that allows it to transition that energy into that intermediate state. And that intermediate state stores that energy in the process of it through the electron.
Got it. Gosh, Julio,
Just a little. No, I thought you would appreciate that.
I do. I can't wait to explain to my family how bone dark looks.
It's one of those funny things. It's like I had a math class. I probably told this story before. And one of the things that we proved in the math class given in a semester was that 1 + 1 is equal to 2.
Yeah.
It took us a long time to get to that. And my professor told us at the end that we should go home to our families and tell them that you're spending $60,000 a year to learn 1 + 1 = 2. That's kind of like this for chemistry, right? You guys spend all this time becoming chemists and all you learn about is glow in the dark stuff.
Yeah.
All right. Okay, it's 3:30. Hi, everybody. Got a little more show up. Actually, it's about the same as last time, so that's good. We got some friends in the chat. Sydney's out today, it looks like. A lot of sick people this week, I think, too. Okay, I want to keep trudging on with atoms. Hey, I want to get us started thinking about atoms with multiple electrons. I posted the last homework for the class. It's on multi-electron atoms. It's working with these term symbols and things like that, right? That's not the hardest math on the problem set. I think there's a couple of, there's one place where you need to do some organized calculations, but they're all just arithmetic and just some numbers. And so you just need to have like an Excel spreadsheet to organize things, but there's no calculus, there's no statistics on this problem set. It's really just multiplication, division, addition, and subtraction. Which is great. That's the kind of math we really want to do in chemistry. So I want to talk again, the whole point why I introduced these term symbols is I want to talk about atoms in a universal way. I want to have a language that allows me to compare atoms of very different type from a kind of a similarity point of view, right? How can we compare how in some sense, how is oxygen fundamentally different from its other atoms? And why, as I described before, we kind of saw in the problems that fluorine and the halogens really aren't that much different spectroscopically from hydrogen, because they all have one unpaired valence electron. Of course, the energies at which all the levels are different, because they're in fluorine, they're n = 2. In the p orbital, hydrogen, they're in the n = 1 orbital, in the s orbital. So there's one unpaired electron. If we excite hydrogen to the p state, then it's in the same state effectively as that fluorine unpaired electron. It's in a 2p state, J3 halves or 1/2. They're really not so much different, and not surprisingly, excited hydrogen, 2p hydrogen, has similar properties to fluorine in its ground state because they have the same electron configuration. So that kind of, and again, that's kind of ties into the fact that hydrogen, if you think about hydrogen as an element that does chemistry, it works both as an acid and a base, electron acceptor, electron donator and electron acceptor. It does sometimes act, it does like to lose that electron to make a proton. H plus is of course the classic acid. But you can also make H minus, right? You can also excite that electron to the 2p orbital, and that has a very, very different behavior. And so excited electron, in some sense, almost acts more like a halogen because of that. Right? So really what the chemical properties of the periodicity of the elements, similarity really come down to the states that the electrons form. And that really ultimately determines their properties. So it's nice to talk about things on the same footing. So I started talking about helium from this point of view. I want to review that discussion kind of in class, and I want to describe why this is an interesting way to analyze helium. Any atom why it's a nice tool because it teaches us to see that helium effectively can be treated almost as if it was two different atoms because of the electronic states of those atoms, of the helium atom, as we'll see. That in some sense the levels split in two. The manifold where you have a bunch of energy levels and another one a bunch of energy levels, and there's really no connections between them. It's as if helium splits into two species. So I want to try that point when we began today. And then we can kind of go from there. We're going to study helium a decent amount over the next few lectures because it's the first element with multiple electrons. So it makes sense that we focus on helium. So let's look at, I want to just look at helium and do an example. He atom. We know what the ground state of this is. It's 1s2. So we've got something that looks like this. Right? And I want to calculate the term symbol for this. Term symbol requires me to think about the possible states that each of these electrons are in, then combine them together, get kind of a total state. So the term symbol, what we need to know is we need to know the total angular minimum L for the system, total spin. We're going to sum over the L's and the S's for the electrons. And then we're going to create a J by combining those two terms. So let's look at that. All right, well, this one's pretty straightforward, right? These are s orbitals, electrons. So for both of these, L is equal to 0. And so if I sum over the L's, I get 0, which is S, right? So we have an S state. And our spins, well, we've got one that's up and one that's down. So we have S is equal to 1/2 plus minus 1/2, right? Because there's one in each direction. So the spins cancel. So the total spin of this system is 0. So we can, now we have all the terms we need. And of course, there's 1 here because we're in the 1 state, 2s plus 1 is 1 because s is 0. L is 0. So this is a 1 and equals 1. 1s 0, right? Because J is 0 plus 0 state. This is our, right? In general, this is the state. The singlet state where all the electrons are in the s orbital, they're all paired. It's the most boring state you could possibly imagine. And we call this a singlet. This is what's called a singlet state. Because again, there's only one configuration of the electrons in the angular minimum. There's just this. That's the only set, just one combination. And so that means there's just one state, therefore singlet. The only state that we can make no other way to combine things together to get a different terms. So helium's got a single ground state. Right? Like a 1s state, it looks just like 1s, but of course now it has 2 electrons in it, right? It's slightly different 1s state than hydrogen, because the hydrogen one has an unpaired electron. It's a spin double. It has 2 states. It has 2 spin states, spin up and spin down. Here, there's only 1 state, right? Because the spin up and the spin down are canceled. So there's only 1 combination. So this is a singlet. Hydrogen's 1s state is a doublet because there's 2 spin states. Okay, so let's excite an electron now. Let's excite an electron now, right? And as we saw before, L has to change by 1. So the first excited state is not 1s to 2s, but 1s to 2p. And we don't even think about the s orbitals when we excite things with light. We start from an s. So we can think about excited helium. So we have an electron here, right? And we bring the other one up to the p state, right? So we have that one, but there's also another possibility, which is spectroscopically forbidden, but it's a perfectly valid state, where I have both of them the same spin. So again, let's do analysis. Right here I have the total L is going to be 0 plus 1, right? Because we have one in L equals 0 and one in the P state, L equals 1. So the total L of this is 1. And of course, that's the same for the other combination, right? They're in the same orbitals. We just have differences of spin, right? So the difference, the way these 2 states that we're going to write them differently is by considering how this total spin is different. Right? So for this state, S is 0. And for this state, S is equal to 1. Or plus or minus. Plus or minus. Because they could both be pointing up or they could both be pointing down. So let's work out the one on the left. That one's fairly easy to do. So on the left, right, we have a n equals 2. So we write a 2 first. We have this total spin is 0. So we have a singlet. The high L is 1. So this is a P state. Right, and what about J? Well, it's pretty easy here. J can either be, right, J, S is 0, so we don't even have to worry about spin doesn't even contribute. There's no L in the 1s state, there's only L in the 2p, so it's the only thing that brings angular momentum to the system is the L of the 2p electron, so J is just 1. Right, so we have a singlet p state on the left. Right, that state is a singlet. That means it isn't magnetic. Doesn't interact with a magnetic field. The electrons are paired. Okay. In fact, this is probably the state we would expect to see when we excite helium from 1s to 2p, right? Because we can't flip the spin technically with light. So we're probably always going to prep this singlet p state. Right? That's going to be the dominant thing that we create with light when we excite it. Now, what about the state on the left, on the right? Right? It's a little more complicated now because we have spins to deal with. Well, no matter what I do, L is always 1 here. There's the only thing that brings up angular momentum, orbital angular momentum to the system is that p electron. We have a p state for sure. Not only do we have a p state, we very clearly have a triplet p state. N equals 2. But what about the value of J?
Wait, why is it a triplet?
Because both of the spins are unpaired. The total spin is 1, right? 1/2 plus 1/2, and we write 2 as plus 1.
Oh, right, okay.
So remember that I said that this state is a triplet. We should have 3 states to pick from, right? So what are those 3 states that we can have? Well, we can have L plus S, which would be J equals 2. So there's a triplet P2 state. All right, here's the second thing. I'm writing on the wrong problem, sorry, I'm writing on the other section's whiteboard. Hold on just a sec. I just got to copy it over. Apologize for that. But remember, when we add angular momenta together, we get everything between the sum of the angular momenta absolute value and the difference of the 2 angular momenta absolute value, different by 1. So the maximum value of J we can get is L plus S, but the minimum value that we can get would be L minus S absolute value, which is 0. And every state is in between is allowed. So there's actually there's 3 states here of different J's. We have the J equals 1 state and the J equals 0 state. All right, so there are 3 states there, a triplet. I don't know how much they're split by. They may not even be relevant, but I do know there are 3 states in an excited state, 3 different J's. Right, so that excited state is in fact a triplet. We would see, if you would predict, it's a little more subtle than this, but imagine that they were all at the same energy. Okay, and we could access any of them equally, and we would look at the intent, the absorption of that line, and then compare it to what the prediction of that absorption line would be for the singlet, right? We have 1 state and we have 3 states. So what we would actually predict is that the intensity of the triplet, all things being equal, would be 3 times stronger because there's 3 times many choices to pick. That's not exactly how it works, though. Because the state that we start at is S0. So J is equal to 0. Right? And if delta L can be 1 and delta S can be 0 in transition, that means delta J can either be 0 or 1, plus or minus. So if I start from the S0 state, even if I can't go into a triplet, assuming I can go into a triplet, I can only access the P0 in the P1 state because J can only change by 1. So that P2 state it's not really immediately accessible, but it's there. This means I can't quite get to it immediately from the ground state. This is actually a really kind of one of those things that not a lot of people have an appreciation for, is that there are many different levels in an energy of a spectrum of a molecule or an atom. And not all of them are immediately accessible by starting at a lower level and going up. Okay. So let's just kind of look at that really quickly. Right, so for instance, if our initial state is 1s0, right? What are our selection rules? Well, delta S can be 0. Delta L can be plus or minus 1. And by definition, delta J can be 0 or plus or minus 1. So if we're at S equals 0, if we're at the singlet S0 state, there's only a selection of states that we can actually excite to. We can excite to with light, only with light in this case. We could accept to a 1p0 state, which doesn't exist. Right? We just calculated that it has to be P1. The other state that we could calculate to is a P1 state. That's allowed, and that exists. Right? That exists. Right? And that's it. Those are the only possible states. So the only transition we would expect to see in our spectrum is just this 1s0 to 1p1. But what I just said is that there's this whole other manifold of states here, these triplet states, that I can't ever access from the ground state. It's just simple as that, right? Because I would have to flip a spin, and that's not allowed. Right? So how would I even be able to access those triplet states? Well, what I would have to do is find some state really high in energy to triplet the flip, and then cool it back down to an intermediate state, to go up and then back down. So like imagine I wanted to get to this 3p2 state. Right? How do I access three P2? Well, I would have to come from above. Right? I would have to come from my source, would have to be something where L is D or P. Right? It would have to be a triplet P1 state, or a triplet D2 state, or a triplet D1 state, or a triplet D3 state, depending on which ones we have. I don't know. Right? And all of these states, right? These states are only available. Sorry, I should say that these are. These states are all in the n equals 3 manifold. Right? We would have to take an electron and put it in the 3p orbital in order to ever get it back into the p states. We'd also have to flip the spin somehow. So it's not easy to get to them, right? We have this whole set of triplet states, which in some sense aren't accessible at all from the ground state. They're just kind of out in the nowhere by themselves. They all exist, but they're not easily accessible, right? We would have to create some intermediate higher energy state and then cool it down to one of these, this triplet p state in order to see it with light. Right, and we can't even, there is this one, for instance, is at n equals 2, but delta n has to be equal to at least 1. So the 2, 3p1 state to 2, 3p2 state is forbidden. Also because L is not changing and delta L is equal to 0. That's not allowed. Okay, so I can't even get, if I ended up in this manifold of triplet states, I can't even move between them. Right. Okay, these states are just kind of locked away in the closet. They all exist, and there's a whole manifold of triplet states for helium. But in some sense, they're completely inaccessible from the singlet side, and vice versa. Triplet helium and singlet helium are, in some sense, two different atoms. They aren't necessarily immediately interchangeable between each other. And if you look at the energy level diagram for helium, I don't want to gain anything from this picture more than just the view that we get from this. So this is an old picture, but it's a reasonable one of the energy levels of helium. On the left, so it's demarcated vertically by a dashed line. The ones on the left are the singlet states, and the ones on the right are the triplet states. As you can see, at n equals 0, the ground level of energy, at n equals 1, sorry, at the ground state is a singlet state. There is no ground state for the triplet state, right? Because the only way to put electrons in a 1s orbital, two of them, is to have them paired, right? There is no triplet state for this ground state. It's just impossible to make one because of Pauli exclusion. So the ground state of the triplet is actually that excited p state, right? That's the first triplet state that can exist. Imagine I created that atom. That atom is always going to be on the right side of this diagram. I'm never going to exchange, it's never going to flip to the other side as far as that, and vice versa. So is it really fair to think about these as the same atom? Well, yes, I guess so, because there's 2 electrons and 2 protons and maybe 2 neutrons. So chemically, it's the same atom, but spectroscopically, it's almost as if there are 2 species there. 2 different heliums that function, that in some sense, they don't even have the same chemical properties, because triplet helium is magnetic and singlet helium is not magnetic. And maybe they have different reactivities. In fact, excited state helium, for instance, can form bonds. Triplet helium can form bonds. So they have different chemistry. So, this is kind of one of the limits of the periodic table. Periodic table does give us some organizational structure. It does help us with our chemistry, but there's, in some sense, even finer demarcations between objects, different elements, based on the states and the configurations of their electrons, because there are electronic configurations that are unique and inaccessible from other ones. So whether you think this is 2 different atoms or the same atom with 2 different faces, I don't know how you can think about it. It really depends on who you ask. When you look at papers, there's other types of examples of this singlet triplet separation. You find it in oxygen, for instance, O2. We'll talk about this in a couple weeks in class. O2, the molecule O2 is a triplet. It's magnetic. And singlet is not reactive. As you guys know, we're breathing it right now. It's mildly reactive. And then there's singlet oxygen, where the spins are paired. It's not magnetic, and that thing reacts like crazy. It's an extremely aggressive oxidizer, singlet oxygen. It will oxidize just about anything. Singlet oxygen will oxidize bare black carbon. It's such a strong oxidizer. I've learned that the hard way, it turns out. So singlet oxygen is extremely reactive, but it's the same molecule as normal oxygen, but you've just split the spin. So is it really the same molecule, or is it a different form? Is it an isomer? It depends on who you ask. Some people often treat these things as separate. Singlet oxygen is different than triplet oxygen. And some people call them spin isomers. They say they're just different isomers of the same molecule. But this is why spin is so important, is it determines chemical properties. Chemical properties can be drastically different between molecules or atoms of the same stuff, but just configured different. What I want to do is kind of summarize these ideas into a set of rules that we can apply to any problem. So I've been talking all about these different term symbols, different configurations of electrons in an atom. The question we haven't really been able to answer yet is, what's the most stable configuration? Well, I guess I can know that the singlet, the S state is going to be more stable than the P state because everything's in an S orbital and a P orbital. But imagine I have a bunch of different ways to configure some set of electrons, and it gives me different term symbols, different ways to configure. We saw that with the P states, triplet P state, right? There's 3 of them. The question we have to ask is, what's the most stable one, right? Because what we're saying is that, yeah, every atom has lots of different ways to configure the electrons, but in general, we generally only see one configuration when we do experiments. In some sense, the atom has resolved itself into some electron configuration that's stable. Some atoms have some mixture in these, but most of the time we know that an atom is a particular state in a ground state. So the question is, how do we determine that? So these rules have been known for a long time, and they help us determine this. So these are called Hund's rules. Hund's rules help us use term symbols to determine stability. Imagine I've measured an atom created a new atom. And I want to figure out what its most stable electron configuration is. In fact, this happens all this, well, it doesn't happen all that much time anymore. We're not making any new atoms anymore. But back in the day, people were making new atoms, and then you would have to figure out, well, what's its charge, right? How many unpaired electrons does it have? Is it magnetic? Is it in a D state? Is it in a P state? Is it in an S state, right? To understand the ground state configuration of a new atom, people have to apply Hund's rules to their data to interpret it. And Hund's rules are fairly straightforward. They're pretty straightforward about how we determine the ranking of stabilities of configurations. And what you're going to see is once we write them down, it more or less allows us to recreate the way that we fill the periodic table of electron filling that we do. It's just a fancier way of doing it. More general. So the first rule is, given configuration of electrons into orbitals, we state with term symbol with the highest value for the what's called the spin multiplicity, which is 2s plus 1. Is most stable. All right, let me show you an example of this. All right, so it says that if you have, imagine I have some electrons and some p orbitals, and I have a choice of whether I pair them or I unpair them. What this is saying is that I want to always unpair as many as possible. I want to have the highest spin. So here's an example of that. All right, let's look at carbon, which is 1s2, 2s2, 2p2. Right? Remember, just like we learn in general chemistry, we don't really care about the orbitals that are filled. Right? They're filled, we just move on. We only care about the valence. So let's think about the 2p2, right? So this is what we would call, right, a p2 configuration. NP2 configuration. You're going to look at these on the homework. Right, so you got 2 electrons in some valence p orbital. What are the different ways that we can arrange, just generally, how can we arrange the electrons in these orbitals? Let's just do the GenChem thing. All right, we've got 3 2p's. Right. One way that we can do it is just pairing them. Another way that we can do it is like this, where they're unpaired. Oops, and then there's one more path where they are unpaired but flipped. Does anyone want to know which one is the correct one?
It's unpaired on the same side.
Start over again. Which one? Number 1, number 2, number 3.
Sorry, number 2.
Number 2, so correct. Right. So by Hund's rule 1, we can already determine, without even knowing that, without even thinking about GenChem. Hund's rule 1 tells us number 2 is the most stable because the first one's a singlet. The second one, of course, is a singlet. And this one is a triplet. Right? So by definition, this one is the most stable. Right? This is the first place winner. And of course, we probably learned that that's the off-bout principle in general chemistry, right? That we fill our orbitals half up before we start to pair the electrons, right? We do up, we have unpaired electrons in each of the orbitals, and then we start to fill them in. Right? Nitrogen has 3 unpaired electrons, oxygen has 1 pair, 2 unpaired, and so on and so forth. All right, so that gives us that determination, right? Right. You might imagine there's some ambiguities, there's some ties that we might make, right? For instance, we're not even sure about these 2 down here. Why is it not Well, okay, actually, so here's another question, right? Between the ones I haven't selected, the two singlets, which one is more stable? That one's not as clear. Not as clear. We need more rules for that. Okay, so let's do that. So for a given spin multiplicity, so triplet, singlet, doublet, whatever, the state with highest L is most stable.
Still can't figure that one out because they're.
Exactly. You can't quite figure it out yet because they're both L equals 1. So not clear yet. What this will tell us, though, is that for instance, if we have a choice between states of 0 angular minimum, 1 angular minimum, 2 angular minimum, the ones of highest angular minimum are always more stable, right? So, for instance, the 1D2 state is more stable than 1S0. So if there's a way to put electrons into a higher angular minimum orbital, they're going to go into that higher angular minimum orbital. The reason why this is, it may not seem rational to you, why it wants to maximize angular momentum. Because we know that the faster the angular minimum is, the higher the energy. But this is contrary to that. What this is saying is that it's lower energy for the electrons to be moving faster. That seems odd, right? The total angular minimum is more stable, higher angular minimum is more stable than lower angular. And that is true for a single body orbiting around a proton. In hydrogen, that's very, very true, right? We want the lower the angular minimum, the lower the energy is. But remember, we'll talk more about this today, we have multiple electrons in this system. And electrons repel each other. So if you have two electrons that are in low angular momentum states, they're a lot closer to each other on average than if you have one of those electrons in a high angular momentum state. So if I have an electron in a D state, it's in some sense swinging further away from the other electrons than it would be if it was in an S or a P state. And so with multiple electrons, the problem, as we'll explore in the next two lectures, is that we have a new energy we have to deal with, which is not the centrifugal force. That's what causes angular minimum states of high angular minimum to be higher energy. But we have repulsion to deal with. And repulsion between electrons is extremely strong. It's equally as repulsive to repel two electrons as it is to attract it from a proton to an electron. It's the same force, but opposite. So when you've got a bunch of electrons contributing and interacting with a given electron, that electron wants to be as far away as possible to lower that stability, that repulsion. So that drives them further out away and drives them into states that are faster orbiting. So they interact with the other electrons less. It's about avoiding each other. So we'll look at that more carefully in the next section. The last one is for atoms with less than half failed valence. The level with lowest J is most stable. Okay. For more than half filled, high J is more stable. All right, it's not immediately obvious how these three rules get me my second place. But you're going to work on that in the talk a little bit more about it. But So what this third thing is saying is exactly the same argument I made before. Which is that if you have a valence that is mostly empty, there isn't a lot of repulsion. So that means that the centrifugal motion of the electron is dominating the repulsion. And so a more stable electron that doesn't have a lot of repulsion is one that's moving more slowly, a smaller J. If there's a lot of electrons in the valence, there's a lot of repulsion, and my claim kicks in again, which is that the electron wants to stay as far away as possible. That means it wants to spin faster, have more centrifugal force, and be further away from the nucleus than the other electrons. So in nearly full filled systems, say like a halogen, where you only have one unpaired electron and seven paired electron, or seven other electrons, six other electrons, the high J state is stable, because that keeps the electron further away.
Okay, but with the example you gave, J is the same for the first and the third one, right?
Not necessarily. Let's work it out. Why don't we work it out? Let's do some analysis and see if we can figure something out. We have to be careful about the numbers. All right, so let's look at this 2p example. Let's just work a little bit of math out. And I'll let you guys finish it. So I want to look at NP2 states. Right. And for NP2 states, we know that the maximum value of L, which is a sum over the electrons of the electron, the L for each electron, right, which is 2 for this system, right, because we have 2p electrons, they're each 1. Each have L equals 1, so the maximum L is 2. And of course, the maximum spin is 1/2 plus 1/2, which is 1, right? So the maximum value of J is 3. So right, so if L is 2, if L is equal to 2, M sub L, M sub big L can be 2, 1, 0, -1, and -2. And M sub S, the total spin projected on the z-axis, can be 1, 0, and -1. Okay, so each electron can be in one of these configurations, and any combination of them. So what I can do is draw a little table of my different states. And start to think about the different configurations that I can make of these with 2 electrons and what the total configuration is. So let's work on that a little bit. Let's play around with this a bit. Give me just a sec. I just got to pull up my notes really quickly. So we can actually combine the electrons in these different states in different ways. Let me just pull my notes up for this. Computer's running a bit slow today. Almost there. Where are we? In orbit. Here we go. Okay, well, what are the possible states that I can get that give me the right set of angular momentums, right? So one state that I could have. So the point is that I want to think about each electron and I want to think about what m sub L state they're each in, and then I want to add them together to get the row and the column. Okay. So these m sub L's and these m sub S's are the sums of the two m sub L's and the two m sub S's of each of the electrons. So I'm going to write the configurations of each electron and that are possible that give me that total m sub S and that total m sub L. Because remember, each electron can be m sub L is a p electron. Let me put it up here. Like each electron can be, right, L sub I is equal to 1, which means m sub little l, which is the projection of one electron on the z-axis, can be -1, 0, and +1. Right, so each electron can bring in 1, 0, or +1 of angular momentum. Right, and so I want to think about the combinations that give me 2 total. So I'm going to write this, my notation here, that I'm going to write for my pair of electrons is going to be L sub 1 plus or minus, depending if it's spin up or spin down, and L sub 2 plus minus. So this would mean m sub S equals plus or minus 1/2. Okay, so I'll put a plus if it's a spin up, plus the minus if it's a spin minus. So the only state that I could get here would be a 1+ state, comma 1+, right? We have 2 electrons and m sub L equals 1. You add that together, you get 2. That satisfies my row. And then I get 2 plus 1/2. That gives me a total m sub S of 1. Okay, 2 plus 1/2 and 2 ones give me 2 and 1. This does not work. Why does this not work? Why is this an invalid configuration for my system? Why can't this work with 2 electrons? What property do electrons have to satisfy?
They have a negative charge.
Let me add, no, a different question. So not worry about charge. Everything's minus 1. No charge. Why is it that I cannot write 2 electrons with the same spin in the same orbital? Why did I never write this? Why didn't I just write it like this? Why is that not allowed? What's that called? You guys learned it in Gen Chem. Why can't I put 2 spin up electrons in the same orbital? You guys remember the name of that?
Forbidden.
It is forbidden. You know the name of that principle is? Pauli exclusion.
Yeah.
Remember Pauli exclusion, and I'll bring it up again. We'll talk about it one more time. Maybe I should have added that as my 4th Hund's rule. No 2 electrons can be in the same state at the same time. Simple as that. Okay, they always have to be in different states. That's why we pair them up and down. We don't pair them up and up because electrons can't do that. So here we have 2 electrons in the same state. Not allowed. Okay, so this entry does not exist. Okay, so there is no state where m sub L is 2 and m sub S is equal to 1. Let's try a different one, right? Let's do the 0. So it's m sub L equals 2. So that means that I have 2 states that are both in m sub L equals 1, but I have them flipped, right? The spins cancel out. So this is a plus and this is a minus. Right? And that's perfectly fine, right? What would this state be represented? This state, let's calculate the term symbol for this. Right? Well, this is L is 2, right? Because we have 1 electron. L is 2, right? Because we have 2 electrons, L equals 1. So this is a D state. It's a singlet. And J here can be 2, 1, or 0. Right, so there's our
Wait, what do you got?
1D2 state. No, it wouldn't make it a triplet, a 1D2 state. Why would it make it a triplet? Because you have a spin up and a spin down.
If there's 3 different states of it, then.
I'm sorry, there's only 1 state.
It's
It's
just 2.
It's just
Okay.
2. It's just 1D2. So this is our 1D2 state. Right, and then I can go down the row a little bit. And the only possible state that I could draw here is 1 minus 1 minus 1, or you have 2 1/2, and of course that's not allowed either by Pauli exclusion. Right? So I can just keep going down this list and coming out with them. And you'll find that some of them have ambiguities. Some of them are multiples. Here's an example. Let's look at m sub L equals 0 and m sub S equals 0. The center one. What are some possibilities? Well, one can be 1 plus, and the other one can be minus 1 minus, right? I could have one electron in L equals 1, ML equals 1, and then one in the opposite orbital going the opposite direction, px and py, if you will, of the opposite spin. Right? Everything cancels out there. The spins cancel out and the angular momenta cancel out. If there's other ways to write it, right, I could write it as minus 1 plus. I could write it as 1 minus 1 plus. I could write it as 0 plus 0 minus. Are those all the possible states? Sorry, this one and this one are the same. So I'll get rid of that one for now. They're the same. But as you can see, there are 3 possible ways for me to arrange the electrons so that the total angular momentum, so that everything matches up. But there's actually a triplet here. Right? And this is a triplet. This is a singlet state, right? Because they're all paired. But as you can see, there are. This is a D state because L is equal to 3. So this is a 1D state, for instance. And so on. And you'll find that there are P states and S states in here as well.
Wait, that's a 1D? I thought that one would be 3D.
Well, it can't be 3D because the spins are flipped. So the total spin is 0. So 2s plus 1. So the only things that are triplets are the triplet note depend is not the fact that there are 3 states there. It's the fact there are 3 different spin states.
Okay.
There's only one spin state here. They're all paired.
Right.
It's just what this means is that either we have what are these? Well, so each of these states correspond to either sorry. One of these states correspond to this one where it's in the +1 and the -1. Another one corresponds to this state where you have one in the +1 orbital and the -1 orbital. And the other one is where they're both in the PZ orbital. Like this. So those are the possible ones. They all have the same m sub L and m sub S. So there's 3 different combinations. Right now, this is the problem. This is why now what I've just drawn here, this doublet, the set of doublets, or sorry, these D states here, are the states where you have 2 electrons that are unpaired but in separate orbitals, and then one where they're paired and then in the same orbital, but only in the L equals 0 orbital. So there's also going to be a state where both electrons are in the same orbital, but not in the M, this is the PZ state, but they might be in the PX or the PY state. Right? So what about this one, for instance? Right, what about this one where this is the PX, this is m sub L equals 1, and this is -1 and this is 0. What about this one? Well, this state would be -1 plus -1 minus. Right? The total m sub L is -2. Right? And so this state would be down here. Right? Down here on the m sub L equals -2, it is a fundamentally different state. But as you can see, it's still a singlet D state. Oh, sorry. I apologize. So let's actually go back to this one right here. Sorry, this state right here, L is 0. So this is a singlet S state. I apologize. This is an S state because it's 0. Okay, so what we find is that when we combine two electrons together in a 2p state, we actually have a big wide range of different possibilities, right? We can get some singlet D states. We can get some S states where the total angular momentum is 0. Everything kind of cancels out. We can also get P states. What would a P state be? Well, that would be where one is in L equals 1 and one is in L equals 0. One's in the Z orbital and one's in the X or the Y orbital. So an example of that would be down here. So like 0 plus minus 1 plus. And then we also have 0 plus 1 plus. Right? That would put us in those two rows. And those are P states, right? Because the total L is 0 plus 1, that's P, and they're triplet. So these are our 3p states. That's right. So this is what makes atomic spectroscopy, one, very interesting, but also somewhat complex, is that you would say, okay, in P2, that means that these electrons are p electrons. Well, that's true when they're by themselves, but when you add them together collectively, they can act like p electrons, but they can also act like an s electron configuration. They can also act like a d one. Right? It depends on if the angular momenta cancel each other out, they add together, or they're somewhat parallel to each other. I kind of think of it that way, right? You starting with 2 electrons at L equals 1, and you can either end up in a state with total angular momentum L plus L, you can end up at L minus L, or you can lead up in a state that's still L equals 1. All those different combinations. So what that makes is that the MP2 state, for instance, with like say in carbon or in oxygen, right, it's much more complex. There's lots of different arrangements of the electrons. And so the states, the structure of the different levels that are available are much denser than you would expect. There's lots of different states, and this leads to all the interesting properties that atoms have. That they can act in some sense differently than they would be if it was just one electron. I'm going to have you guys play around with this in a homework, very, very simple experiment. Just kind of adding and subtracting numbers together. Okay. What time is it? Okay, we got 15 minutes left. Great. So we're about just like half a lecture behind the other class. What I want to talk about now is I want to step away for a moment from states and quantum numbers. And I want to think about going back to the original problem we had, which was our original goal. But yeah, basically, well, you got the right idea, right? The idea that ultimately our goal in this class was to define problems and solve the equations of motion, define wave functions and energies and all the properties, right? We did for particle box harmonic oscillator, the hydrogen atom. We had all of these successes where we could come up with really useful models and quantitative models to look at chemical properties. So now our task is, and the way that we always did is we started with a simple problem and we made it a little more complex, right? Particle in a box, you start a particle in a box, and then we made the box leaky, or we made it 3 dimensions. Harmonic oscillator, we made the oscillator and harmonic. Maybe we thought about a system that has many oscillators, right? A polyatomic molecule. Right? We took our basic model and we expanded it to something more complex. It's time to do that now for hydrogen. Right? We have this appreciation for hydrogen. We know we can solve for hydrogen exactly. And what I've just done for the last 2 lectures is qualitatively use the knowledge we took from hydrogen to start building up a qualitative theory for the rest of the atoms. Right? We get Hund's rules and we get all these different spin states and all these isomers and things like that. This all just comes from our spin orbit analysis of just hydrogen. So now let's go back to the original question that we always pose, is can I use the results of hydrogen to bootstrap my way into understanding the results for helium. If I can solve hydrogen, can I solve helium? And in some sense, you can think of almost, like helium is like two hydrogen atoms smushed together. Because it has a nucleus of two protons and it has two electrons. So really what you can think about that is it's like two hydrogen atoms that have been smushed together and a couple of neutrons have been added to the core to stabilize it. So what if I treat the system like that? What if I tackle helium from the point of view of two smushed hydrogen atoms? Do I get the right answers? So that's what I want to explore today. Like every problem that we've come across, we find that yes, we can maybe do something like that, but it gets a little funky and we have to make some corrections. And so I want to look at those corrections, and what we're going to find is that actually those corrections, the reason why helium isn't actually two smushed hydrogen atoms put together is actually in some sense very, very instructive about the structure and the behavior of a multi-electron. So what we're going to see is we're going to fail. And we're going to find that the failure of this calculation is more instructive than if it were actually to succeed. Which seems odd, but how it works. We're not going to be able to do all of it in 10 minutes. So I just want to set the problem up now. And then we'll resolve the problem on Monday. Okay, so let's think about the helium now. Right, we're going to find, again, what we saw qualitatively is I can come up with a theory that at least qualitatively allows me to talk about any atom I please. It has to do with the valence. So hopefully, quantitatively, I get the same results. So let's set up our helium atom exactly the way we set up our hydrogen atom to begin with, right? Let's draw a little coordinate diagram of all our particles and think about forces between them. All right, so here's my three-dimensional coordinate system. In the center, we're going to put our nucleus. Right. Of course, now the nucleus of helium has two protons and two neutrons. Right, so this is actually P plus neutron, PPNN. Right, that's helium-4. There's also PPN, helium-3. That's also an atom. An isotope of helium is extremely rare. It is naturally occurring, but incredibly rare. So we typically just think about helium-4. And now we have two electrons to track. So we're going to have one electron at E1. Or sorry, electron at R1, electron 1 at R1. And just some other electron pointing out at some distance R2. That we can track, which we can call E2. All right, there's our helium. Two electrons and a nucleus that sits in the middle with two tracks. All right. Let's think a little bit about what forces are being felt. So let's do exactly what we did in hydrogen. Right, let's add our forces and our potential energies together. So our helium Hamiltonian. First, we have kinetic energy. Right? We have the kinetic energy of the nucleus. We have the kinetic energy of electron 1. And the kinetic energy of electron 2. Right? Those are our three kinetic energies. We can neglect the nuclear kinetic energy because we're doing motion relative to the nucleus, right? Remember, our nucleus is a fat elephant with a bunch of flies. We can treat the kinetic energy of the nucleus to be 0. We don't have to worry about it so much, at least in this case. Okay. Right, and these two leftover kinetic energies, they're just functions of R1 and R2. Right? They're just about the positions and the velocities of each electron. Right, so this is a function of R1, and this is a function of R2. Okay. two electrons have independent motion. Those are our kinetics energies. We also have potential energies. What are our potentials? Well, we have the electrostatic potential between the nucleus, which is PP, and electron 1, right? So we have that electrostatic attraction between them. We have the electrostatic attraction between the nuclei and electron 2. Right? But we have a new term that we haven't dealt with yet. Right? There's another interaction, which are the interaction between the electrons. Slightly different. We have a third term now, which is the interaction between E1 and E2. Okay. So we should define, remember that the attraction, electrostatic attraction to two objects of a charge depends on the distance between them. So let's define a distance between the electrons, which I'll call R12. And I'll define R12 to be the absolute value of R1 minus R2, which is the way that I would construct that vector from those vectors. Okay, and let's think now about what coordinates do these depend on? Well, the potential for E1 and the protons is just the distance between them. So this is an R1. This is just dependent on R1. This one is dependent on R2. But this interaction term between the electrons is dependent on both. Right? Because I can have, imagine R1 and R2 are the same length. That means that both electrons feel the same attraction to the proton. But imagine that the two electrons are on opposite poles. And that means the repulsion between them is much less than if they were right next to each other. Right? So what that means is that the energy of one electron depends on the position of the other, and vice versa. Notice that if I turn, right, so this is important, is that this is a repulsive term. Right, and what it does is it causes my Hamiltonian to be dependent on both coordinates in a dependent way. If I turn that term off, I have two kinetic energies and two potential energies that are completely separate from each other. Right, I've got two terms for one electron, two terms for the other electron. It's almost as if they aren't even interacting with each other. So if I turn that off, all I can say is that the helium Hamiltonian looks like the Hamiltonian for hydrogen, one hydrogen atom, plus the Hamiltonian for another hydrogen atom, right? Because the hydrogen atom is just a proton and an electron. And basically I have a motion and potential for one electron with a nucleus and another electron with a nucleus. So they're just separate. And I have to multiply, because of the charge, by z squared. Oh, sorry, actually, I don't want to write that yet. I'll take that back later. I don't want to say that yet. Right, and so what this is saying is that if I turn that repulsion term off, I have a separable Hamiltonian, separable energies. Right, just like some of the 3D particle in the box sphere in problem set 2 we did, where each of the directions were independent of each other, x, y, and z are all independent coordinates. And so the Hamiltonian of the particle in the box is just the sum of the x plus the y plus the z. And that led to a wave function that was the wave function of the x times the y times the z. So we have a sum of electron 1 plus electron 2. That means that in this.
Wait, so that instead of H1 and H2, it's supposed to be E1 and E2, right?
Yeah, sure. For a hydrogen atom. Yeah, sure. If you want to write it like that. I'm saying it's exactly the same term, it's exactly the same Hamiltonian you would have for a hydrogen atom.
I see.
But now we have two of them because there's two electrons. And so you could say that the ground state wave function for helium looks just like a product of 1s orbitals for hydrogen. Right? There's just two of them, one for each electron. I call them 1 and 2. Okay, so that's the idea, right? The idea when I want to test is to treat helium as two hydrogen atoms smushed on top of each other. Right? That's all I'm saying here, right? Which two hydrogen atoms smushed on top of each other means we have a nucleus of charge 2 and two independent electrons that are just moving through around that. And they don't interact with each other. So this is a smushed hydrogen approximation. Smush two hydrogens together to see if we get a nice approximation for helium. Right? I don't know if this works or not, because I don't know what the size of that repulsion is. So we'll have to think about that, right? We'll have to consider how important that repulsion is and whether it's valid for me to turn on or off. But let's just start with the simplest problem. We already know how hydrogen works. So let's turn it off and let's just calculate something. Right? Because we know how hydrogen works, we can calculate how two hydrogens work together. Okay, so this is what we're going to call the orbital approximation. Right, which is the idea that I can treat, what we say, at zeroth order, at simplest level, each electron in an atom acts or can be represented or can be approximated using the results for a hydrogenic electron. Right? So each electron, I can just assume they look like hydrogenic electrons.
Wait, this is what we did in the homework. Right? Report. It's like.
Yes, yes, that's similar. Yes, that's the same idea. We're doing a slightly different problem than that, but you have it comes from the same concept where we're taking properties of hydrogen and extrapolating them to larger systems. We're doing the same thing here. What we're doing is we're assuming that we have an atom with n electrons, and we're going to treat it like we've taken n hydrogen atoms and smushed them all together. Okay, so what we're going to do first is assume the potential energy, which is a function of the distance between the electrons, is effectively 0. So no electron repulsion. We're going to finish this slide up and then we're done. It's going to take me just a second. Easy calculation. All right, so that means then the idea is that we can guess the helium wave function, which is a function of R1 and R2, as being equal to a wave function for hydrogen for the 1s orbital centered at R1 times a wave function of hydrogen centered at R2. Okay, so these are just 1s hydrogen orbitals. Right? And if you remember correctly, we didn't really talk about this too much. This kind of looks like e to the minus R2. It's an exponentially decaying function. All right, what this means then is that the guess energy of helium is going to be equal to the energy of one hydrogen atom at some state N1 plus the energy of the hydrogen atom at some state N2, right? These are ground states, so N1 and N2 are 1. Okay. And so that's going to be minus, we have 13.6 EV.
times 1 over n1 squared plus 1 over n2 squared. And then we have to multiply by the square of Z, which is the charge. Of course, for helium, that's the number of protons. It's the number of protons, which is 2 for helium. And so N1 and N2 here are 1, so this just goes away over here. So this just looks like 4 times, well, sorry, I forgot a minus sign. Minus sign on the outside. Negative. Minus 4 times 13.6, right? Remember minus 13.6 was the hydrogen ground state. 1s was at minus 13.6. So this is just 4 times that because there are, oh, sorry, it's not that, it's 8 times that. Yeah, it's 8, is it 8 times that? See, we have 1 over 1, that's 1 plus 1, 2. Yeah, so it's 8 times that. Right, so that's 8 times 13.6 EV.
Times 2 also, right? Because 1 over n 1 squared plus.
Well, I've already counted that. Z is 2, so 2 squared is 4, and then I have another factor of 2, so it's 8.
Oh, right, okay.
Okay. So this says that the prediction is that the energy of the helium ground state is at a minus 109 EV, give or take. Okay. So what does this number tell me? Well, this number tells me how much energy it takes to remove both electrons from the ground state. All right, so what we can do is we can go look at the ionization energies of hydrogen. And I know that if I got this answer right, it takes that much energy to remove both electrons. I'm just going to show you the result, copy it over, and then we can talk about it next class. So experiment. So here's the experiment. All right, to take the first electron out of helium, it takes about 25 EV. To say take the second one out of the helium cation, right? The second ionization takes another 54. So the total ionization energy of helium is 79 EV. We predict it to be 109 EV. We're off by 40 EV. So the error is 40 EV, which is about it's about 1.5 times the ionization energy of hydrogen. I would call that a huge error, right? We're off by 1.5 hydrogens worth of energy. All right. I put a quote here from my high school chemistry teacher, which is a quote he gave me when I got a C on my kinetics exam. He said, I can guess better than that. I can guess better than this. So we've got a problem. What this is telling me is that the smushed hydrogen approximation doesn't seem to be working the way that we would like it to. Okay, but we've neglected 2 things. One is we've neglected the repulsion, and we've assumed that it's 2 hydrogens smushed together. So what we're going to do is we're going to kind of smooth those assumptions out and try to do a slightly more complex calculation, including repulsion, and see where we go from there. Right, that's where we're at right now. You guys have a lovely weekend. I'll see you on Monday.
Yeah.